Welcome to Course 4, Module 2, Chapter 5, Sustainable Sourcing and Circular Supply Chains. This session explains how procurement becomes a central lever for decarbonization, resilience, and long-term circular viability. We will move beyond the traditional view of purchasing as a cost reduction function. Instead, we will see procurement as the function that selects materials, suppliers, contracts, and data systems that determine whether resources can circulate safely over many life cycles. The chapter also connects circular sourcing with secondary material markets, localized supply networks, Scope 3 emissions, supplier scorecards, and chemical governance. By the end, you should understand how sourcing choices shape both environmental performance and operational stability. We begin with the overall shift from linear, cost-focused procurement towards circular supply chain viability. Then we examine how organizations can procure circular materials at scale, especially when recycled and bio-based inputs face uncertain quality, volume, and prices. Next, we review economic models that explain volatility in secondary material markets. The middle sections connect sourcing geography with emissions and geopolitical risk, then introduce scorecards for supplier circularity and resource efficiency. We then integrate Scope 3 emissions into supplier selection. Finally, we address hazardous chemicals in closed loops, compare Apple and Tesco as practical gatekeeping cases, and close with the main conclusions. This introduction frames procurement as a design function for circular supply chains. The key question is whether sourcing choices support safe, repeatable material loops rather than only short-term savings. Procurement must move from cost minimization towards circular viability. In that role, it becomes a strategic architect, because it designs material loops, reverse flows, and industrial symbiosis instead of merely buying inputs. It also becomes a gatekeeper, because it decides which suppliers and materials are circular-ready enough to enter the network. Finally, procurement becomes a policy-linked lever, because contracts can include life cycle criteria, performance-based requirements, and take-back obligations. The important point is that circular supply chains are not created after purchasing. They are created through purchasing choices that shape the entire material life cycle. This reframing explains why the procurement role becomes strategically important. Here we see that circular procurement supports several different loops at the same time. Closing loops means sourcing recyclable or remanufacturable materials and arranging take-back systems. Slowing loops means buying durable and repairable products that stay useful for longer. Narrowing loops means reducing the amount of input material needed for each unit of value. Dematerializing loops means replacing physical products with services or digital alternatives when appropriate. Intensifying loops means improving utilization, so assets are used more fully. Procurement orchestrates these possibilities through supplier specifications, contracts, and relationship choices. The sourcing decision therefore determines whether materials can loop safely, repeatedly, and economically. Each loop requires different supplier evidence and contractual commitments. This table translates circular economy ideas into practical procurement levers. For closing and looping, the objective is to retain material value, so sourcing must include recyclable inputs, remanufacturable designs, take-back agreements, and reverse logistics. For slowing and extension, procurement emphasizes durability, reparability, service contracts, and maintenance arrangements. Industrial symbiosis asks buyers to treat residuals and byproducts as potential inputs across different supply chains. Regenerative cycles focus on bio-based, non-toxic, and pure materials that can safely return to biological or technical systems. The message is that procurement criteria must expand. Price, quality, and delivery still matter, but circular readiness becomes a core sourcing requirement. Together, they turn circularity into procurement practice. This section examines how procurement secures circular materials at scale despite uncertain volumes, variable quality, price volatility, and contamination risks in recycled, upcycled, and bio-based input markets. Secondary material markets often behave differently from mature virgin material markets. Recycled inputs depend on uncertain waste returns, variable sorting quality, and fluctuating spot prices. This slide shows one response. Reserve recycler capacity in advance, then use virgin spot purchases as a buffer when recycled supply is insufficient. The goal is not to abandon virgin materials immediately, but to use them strategically while increasing recycled content. Capacity reservations lock in future processing volume, spot buys protect against shocks, and the combination makes circular sourcing more financially stable. This approach allows procurement to scale recycled inputs while reducing exposure to both quantity shortages and sudden price movements. This is a controlled transition, not an immediate substitution. Volume is only one part of circular material procurement. Quality is equally important, because recycled and upcycled inputs can be contaminated, inconsistent, or difficult to trace. This slide shows two complementary approaches. First, quality-centered multi-sourcing evaluates both the physical quality of the material and the relational quality of the supplier. Strong relationships can create a buyer-supply surplus, meaning the buyer may secure better quality or lower prices through trust and collaboration. Second, firms may integrate upstream collection and sorting more directly. Proprietary trading points, targeted training, and close interaction with informal or fragmented networks help prevent contamination before materials enter the recycling chain. This makes quality prevention cheaper than downstream correction. This slide condenses circular input procurement into three logics. The first is to lock in volume through capacity reservations and hybrid sourcing, which protects against volatile return flows and uncertain yields. The second is to compete on quality through structured bids that evaluate supplier reliability, material performance, and relationship strength. The third is to own or tightly manage the upstream interface, especially where collection and sorting are fragmented. Procurement can also use recycled content thresholds, clean cycle requirements, life cycle costing, and take-back schemes. Together, these logics show that circular sourcing is not one tactic. It is a portfolio of contracts, controls, and supplier development practices. It also clarifies where procurement should focus managerial attention. This section explains why secondary material prices are volatile and how policy models, sourcing models, and system dynamics help procurement anticipate instability instead of reacting too late. This slide introduces the three modeling lenses in more detail. Partial equilibrium models look at market-wide relationships between primary and secondary materials. They help explain the effects of virgin material taxes, recycling subsidies, and tradable credits. Inventory and sourcing models operate at the firm level. They use news vendor-style logic to decide how much recycled capacity to reserve and how much spot purchasing flexibility to keep. System dynamic simulations add time, feedback, and structural change. They show how dismantlers, recyclers, policy support, and investment decisions can create endogenous volatility. The key takeaway is that secondary material prices are shaped by policy, physical flows, capacity, and substitutability. Procurement can then plan contracts with better realism. Policy instruments can change both price levels and volatility in secondary material markets. A virgin material tax raises the relative price of virgin inputs, which can encourage firms to shift toward recycled materials. However, the effect may be limited when buyers have low price sensitivity or when recycled materials are not close substitutes. Recycling subsidies or credits work differently. They increase secondary supply, support recycling capacity, and may lower or stabilize scrap prices. The slide also highlights substitution quality. If secondary materials cannot fully replace virgin inputs, price signals are dampened. Thin markets, high transaction costs, and information asymmetry can still amplify volatility, even when policy support exists. Policy design therefore matters directly for sourcing strategy. This section connects sourcing geography with decarbonization and resilience. Localization can reduce transport emissions and geopolitical exposure, but it must be balanced with cost, capability, diversification, and redundancy. This slide frames localization through two pathways. The decarbonization pathway begins with shorter transport chains, which reduce carbon dioxide per unit shipped. Localized networks can also relax just-in-time pressure, making slower and more fuel-efficient transport modes possible. Greater geographic proximity can improve visibility and supplier sustainability monitoring. The risk management pathway focuses on exposure. Local or near-shore suppliers can reduce vulnerability to border closures, geopolitical shocks, and long lead time uncertainty. A total cost perspective is important here, because the cheapest offshore price may hide disturbance costs, compliance risks, and inventory buffers. Localization can therefore serve both climate and resilience goals. These benefits should be tested with evidence, not assumed. This slide explains the emissions mechanism more directly. Local or near-shore production places materials closer to end markets. Shorter distances reduce transport emissions per unit. When lead times are less extreme, companies may also reduce strict just-in-time pressure and choose slower, more efficient transport modes. These changes lower freight activity emissions beyond the simple distance effect. However, the caveat is important. Empirical research suggests that firms often reshore primarily for risk, reliability, cost of disruption, or strategic control, not purely for environmental reasons. In practice, emissions reduction may be a valuable co-benefit. Procurement should therefore evaluate localization through both carbon data and risk-based total cost analysis. This slide shows why resilience requires mixed configurations. Onshore sourcing may reduce some border risks, but it can create new dependence on one domestic region. Nearshore sourcing may balance proximity and cost, while offshore sourcing may still provide capacity, specialization, or material availability. A resilient network combines these options through multi-sourcing, diversification, and redundancy. The lesson from recent shocks is that concentrating supply in any single geography can be dangerous, whether that geography is far away or close to home. Procurement should design an optimized network that balances cost, emissions, lead time, capability, and the probability of disruption under changing conditions. This section turns circular ambition into measurable supplier evaluation. Scorecards help procurement compare resource efficiency, circular maturity, reverse logistics capability, eco-design, and supplier development needs. This slide shows the basic scorecard workflow. First, procurement defines circular economy criteria, such as resource loops, reverse logistics, eco-design, recovery practices, and recycled content. Second, the organization weights trade-offs across environmental, operational, and social dimensions. Third, suppliers are scored and ranked according to circularity, maturity, and resource efficiency. Finally, the results are used in contracts, supplier development plans, and relationship management. The key point is that measurement is not an academic exercise. A scorecard should help buyers decide which suppliers to select, which suppliers need improvement, and where collaboration or investment will create the strongest circular performance. It also makes supplier discussions clearer, more objective, and easier to audit. There are several methods behind circular supplier scorecards. Fuzzy multi-criteria decision-making methods, such as best-worst method, TOPSIS, VICOR, and CRITIC, are useful when supplier data is uncertain or partly qualitative. Data envelopment analysis, or DEA, converts groups of performance indicators into relative efficiency scores. Maturity indices separate actual circular performance from the organizational maturity needed to sustain that performance. Balanced scorecard and supply chain operations reference structures embed circular indicators into familiar governance systems. Combined, these tools help procurement transform complex supplier information into reliable ratings and rankings for strategic sourcing, benchmarking, and continuous improvement. That evidence can then guide selection, contracting, and continuous supplier development. This slide focuses on what procurement can actually measure. Useful circular metrics can include recycled content, material intensity, waste generation, energy use, recovery rates, product repairability, reverse logistics capability, and compliance with non-toxic material requirements. Some frameworks measure performance across the product lifecycle, while others assess supplier maturity, data quality, or resource efficiency relative to peers. The important point is that no single indicator captures circularity on its own. Procurement needs a balanced set of metrics that reflects both environmental outcomes and operational capability. When these measures are integrated into supplier audits and scorecards, circular economy principles become part of everyday sourcing decisions. The metrics should remain practical enough for repeated procurement use. This section shows how Scope 3 emissions can become supplier selection criteria, despite imperfect data. Procurement links climate targets to sourcing decisions through carbon metrics and decision models. Why Scope 3 targets are difficult to translate into supplier criteria. The first challenge is data quality. Many calculations rely on secondary emission factors, while supplier-specific primary data is incomplete. The second challenge is method variance. The Greenhouse Gas Protocol allows multiple calculation approaches, which can make suppliers difficult to compare. Third, information asymmetry is common, especially among lower-tier suppliers that lack measurement capability. Fourth, large supplier bases limit buyer influence and make engagement difficult. The implication is not that procurement should ignore Scope 3. Instead, it needs decision models that explicitly handle uncertainty, uneven maturity, and imperfect comparability. These limits make structured judgment especially important. This slide shows how carbon can be embedded into supplier selection. The process begins with supplier data, using primary emissions data wherever possible and secondary factors where necessary. Carbon then becomes a formal criterion alongside cost, quality, delivery, and social performance. Decision models, such as fuzzy multi-criteria approaches or optimization models, can evaluate trade-offs under uncertainty. Target pathways based on multi-region input-output analysis provide benchmarks for sector and country-level emissions intensity. Finally, procurement prioritizes engagement where decarbonization impact is highest. This turns a broad climate target into a structured sourcing decision, linking supplier selection with measurable emission reduction pathways. This approach supports prioritization when resources for engagement are limited. This section highlights a hidden risk of circularity. Hazardous substances can also circulate. Safe closed loops require traceability, testing, decontamination, and supplier evidence before materials re-enter production. Unknown composition is a major problem because chemical information is often lost when products become waste. Contaminated feedstock then spreads substances across new product generations, especially when diverse waste streams are co-recycled. These contamination risks create business consequences, including non-compliance, recalls, reputation loss, worker exposure concerns, and reduced customer trust. They can also create stranded circular assets if future regulations restrict materials that were once considered acceptable. The policy conflict is clear. High recycling rates are desirable, but they can clash with the goal of a non-toxic environment. Procurement must therefore treat material purity as a circularity requirement over time. Chemical governance must close three gaps. The traceability gap concerns knowing what substances are present before products become waste and before recycled inputs re-enter production. The quality assurance gap concerns funding and specifying sorting, testing, and decontamination protocols that make secondary materials safe enough for use. The regulatory gap concerns aligning waste, product, and chemicals rules so that secondary materials are not governed by weaker or confusing standards. Procurement can respond by specifying non-toxic inputs, requiring supplier evidence, using approved formulations, and building chemical safety clauses into circular sourcing contracts. Without these controls, closed loops may simply circulate hidden hazards. The safest loop is one where hazards are excluded early. This section compares Apple and Tesco as proactive chemical management cases. Both show how procurement can act as a gatekeeper, preventing hazardous substances before they enter products or production processes. This comparison shows two gatekeeping models. Apple's objective is final product safety and component purity. It uses a proprietary regulated substances specification, enforces restrictions at the homogeneous material level, and requires third-party laboratory reports showing substances are below detection limits. Tesco Florence and Fred focuses on facility-level discharge and safe wet processing. Its approach aligns with the ZDHC manufacturing restricted substances list, controls chemical purchasing through approved formulations, and verifies performance through the ZDHC Gateway Plus wastewater testing. The reported results are significant. Product chemical failure rates fell from 1.1% to 0.4%, and targeted hazardous chemicals in wastewater declined by 6 to 14%. The conclusion brings the chapter together around 5 messages. First, procurement must design sourcing decisions around circular material loops, not only around short-term cost. Second, stable circular inputs require hybrid sourcing, recycler capacity reservations, quality controls, and strong upstream relationships. Third, localized sourcing can reduce freight emissions and geopolitical exposure, but it should be combined with diversification and redundancy. Fourth, supplier selection should use circularity scorecards and scope-free data to compare capability, maturity, and carbon impact. Fifth, chemical governance is essential because closed loops can recirculate hazardous substances unless procurement requires traceability, testing, and supplier verification before materials enter the loop. Together, these messages define procurement as a strategic circularity function. Thank you for your attention. Next, we continue with Module 2, Chapter 6.